Good day everyone, I'm Fabiano Bersabal Jr. and today we are going to discuss about the equivalent circuit of a practical or real transformer. First, let's find out what is a transformer. Transformer is a static device which transfers electric energy from one circuit to another through the process of electromagnetic induction. Transformer is commonly used to increase or decrease voltage level between circuits. Before we proceed about real transformer, let us recall first our previous lesson, which is about the ideal transformer. Ideal transformer is a transformer which is free from all types of losses. And these losses are copper losses, leakage flux, reluctance, and iron losses including hysteresis losses and eddies current losses. So the equivalent circuit of an ideal transformer is look like this. Now let's talk about the real transformer. Real transformer is made up with this assumption. First, it has copper losses since the windings are electrical wire with resistance no matter how small. So, copper losses are losses due to the resistance of the windings of the transformer, both the primary and the secondary windings. So, this resistor R1 and resistor R2 represent the copper losses of the practical transformer. So, the second assumption is it has core losses due to eddy currents and hysteresis losses. So, eddy current these are resistive losses in the core of the transformer which dissipates as heat. It is equal to the square of the voltage applied to the transformer. And the hysteresis losses, since the core of the transformer is ferromagnetic material, the magnetic domains will tend to align with the magnetic field produced when current flows through the windings. So, this resistor RC and inductor XM, which is parallel to each other, represent the eddy currents and hysteresis losses. So, the next assumption is the leakage flux. So, leakage flux are fluxes that not pass through the core, which will produce a self-inductance in the primary and secondary coils and should be accounted for. So, this inductor X1 and inductor X2 represent the leakage flux of the practical transformer. And lastly, the last assumption is the secondary winding has more turns than the primary winding. Now, let's move to self-inductance. The self-inductance of a transformer is the net inductive effect reflected into the primary circuit by the transformer, and it is also the sum of the primary voltage due to neutral flux and the primary voltage due to the leakage flux. So this type of inductance modeled as an inductor. Now let's move to core excitation effect. In core excitation effects, there are two categories. First, the magnetization current. Magnetization current is proportional to the applied voltage and is lagging by 90 degrees. So it can be modeled by a reactance X sub M across the primary voltage source. Next is the core losses. Core losses is proportional to the applied voltage to the core that is in phase with the applied voltage source. So it can be modeled by a resistance, the equivalent circuit of the practical transformer. Next is the impedances. As you can see, there are two examples of equivalent circuit of a practical transformer. On this side, the equivalent series impedance referred to the primary side. Notice that these components here above is connected to each other. So it means that the Z equivalent is just the sum of all of these components. With that, you can get a formula of Z equivalent is equal to Rp plus A squared times Rs plus J times Xp plus A squared times Xf. Now, on the other side, the equivalent impedance referred to the secondary side. You just divide the impedance components by A squared and you can get the formula directly. And with that, you can get a formula of Z equivalent is equal to Rp over A squared plus Rs plus J times Xp over A squared plus Xs. You just divide these components by A squared and you can get directly the formula if you base to the secondary winding.
Now let's have some example. The equivalent resistance and reactance of 50 kVA 2400 to 480 volts transformer windings are is equal to 2.8 ohms and X is equal to 6 ohms. High side, a load of 10 angle 20 degrees is connected to the low voltage side. Determine the equivalent impedance of the transformer and load combined. Now feel free to pause the video and solve for the unknown. Now here is our solution. Based on the given, we can form an equivalent circuit and it is look like this. First thing to do, we need to find our turns ratio. Our turns ratio is equal to Vp over Vs. Our Vp is equal to 2400 volts and our Vs is equal to 480 volts. Therefore, we can get a turns ratio which is A is equal to 5. Now, we need to refer Z load to primary side. So, we don't need to worry about this Z equivalent because we know that the Z equivalent is just the sum of these two components. Our problem here is the Z load high side. To find this Z load high side, we have a formula. Z load high side is equal to A squared times Z load. Z load high side is equal to 5 squared times 10 angle 20 degree. And we can get an answer. Z load high side is equal to 250 angle 20 degree. Now to find the Z equivalent impedance, we just add these two components value. This and if we add them using our calculator, we can get an answer of 254.7 angle 21.05 ohms. And now this is our final answer. That's all for today, and I hope you understand. Thank you for watching.